All right, you ready? As I drop everything. Okay. And I'm also probably just gonna do an intro. Okay. Hello, everybody. My name is Abby Carbone. I am a graduate student here at Stanford University in Material Science and Engineering. And also here with my demo, we have some audience members. So these are some undergraduates here in Material Science at Stanford, here to kind of help us out with this demo today. So if you hear some feedback back and forth from the audience, that's going to be our lovely undergraduate students. Woo! Yeah! I also want to pan over our awesome audience. Wave hello, you guys are great, yay! Hooray! And today we're going to do a liquid nitrogen demo. But before we get to that, I want to first explain what material science is, because as a material scientist, that's actually the most frequent question that I get asked is, what even is your major? When I first heard about material science, the first thing that I thought of was textiles, was clothes. But that's actually a whole separate major. In material science, when I say the word material, what I think are things like metals, like plastics, like polymers or ceramics. So if you look around you and you see anything that's made by a human, that is material science. A material scientist made that. And so what we do as material scientists is not only do we create everything that you see around you, but what we do is we take a material, we study it, we quantify its properties, we see how it behaves if we stretch it or bend it or break it or whatever, and then we change its environment. So maybe I heat it up, maybe I cool it down, maybe I apply a voltage or a current, maybe I throw it up into outer space, what have you. So we take a material, study it, we study its properties, we change its environment, and then we see how those material properties change as a result of changing their environment. So maybe if I heat it up or apply a voltage, it makes it easier to bend or stretch. So that's kind of what we're going to be exploring today here in this liquid nitrogen demo. So the first kind of material that I'm going to introduce to you today, this is called a polymer. So for my material scientist undergrads, can someone tell me what a polymer is? Anyone know?
It's a long chain of a molecule or an atom.
I agree with you. I would say kind of the more intuitive way to think about a polymer is I actually like to think about it as spaghetti. So you can think about a lot of kind of cooked spaghetti noodles all intertwined and all meshed together, right? But we also know that the kind of colloquial name for a polymer is called a plastic. So we know that not all polymers are nice and squishy and bendable. You have your silly putty or you have your plastic bags or whatever. Those are nice and stretchy, but I also have my safety glasses, which are nice and hard, which is why spaghetti is also another great example, because you can have cooked spaghetti or uncooked spaghetti. And you can also throw in lots of stuff. You can throw in pasta or meatballs or veggies or whatever. And scientists do similar things, but with different atoms and different elements and different molecules instead of, vegetables or whatever. So if we take, if I take this polymer racquetball and I drop it, what will happen? Ideally not.
Hopefully.
Hopefully not. Do we have any other guesses, or does everyone here think it's gonna explode?
It'll bounce.
It's gonna bounce, obviously. Maybe it'll explode, who knows? Okay, so no explosions here today. So if I take this racquetball, this polymer racquetball, and I drop it, we know that it's going to bounce, as we have just shown, and it's not going to explode. But like I said, we're a material scientist, right? We're materials engineers, and we want to study materials and do experiments and see how the properties change as a result of doing those experiments. So that's exactly what we're going to do today. Okay. So here, in this doer, I have something called liquid nitrogen. Does anyone here know what liquid nitrogen is? Panic. It's really cold? It is really cold. So we know that nitrogen makes up, does anyone know what percentage of our atmosphere is from nitrogen?
70.
70? Yeah, it's actually 70%. Yeah, it's like 70 or 80. So most of our atmosphere is actually nitrogen. And we know that since nitrogen is a gas, if we want to make it into a liquid, what do we have to do to it? Cool it down. And so if we take our nitrogen that we have in our atmosphere, it turns out that we have to cool it down very, 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 very cold in order to make it have that phase change from a gas to a liquid. Does anyone know how cold liquid nitrogen is? Cold? You're not wrong.
Isn't it -170 Celsius?
Negative 170 Celsius? I actually don't know what it is in Celsius. I know what it is in Fahrenheit.
Just threw that out now.
Liquid nitrogen is a whopping negative 321 degrees Fahrenheit. And for those of you at home who have never used liquid nitrogen before, never seen it before, what I'm actually wearing right now is cryoprotectant gear. So I've got these nice cryo gloves because your finger would be very frozen and very sad if you put it in liquid nitrogen. So that's bad news bears. And then I've also got these safety glasses because liquid nitrogen is cold and if it splashes in your eyes, that's also bad news bears. So while I'm waiting for our racquetball to cool down, like I said, we're scientists and we're engineers. And as we do experiments, we like to make observations. So one observation that I'm going to make is we've got all of this like mysterious white cloud gas vapor going on. Does anyone know what this is? This up here?
Gaseous nitrogen.
Gaseous nitrogen. Remember earlier when I said that our atmosphere is made of 70 to 80% nitrogen. So if this was gaseous nitrogen, that wouldn't really make a whole lot of sense because that would mean we would be looking around and walking around and seeing just a white cloud of smoke everywhere. I've said the words cloud and vapor enough times though for you guys to get the hint.
Is it water?
It is water. It is water. Yeah, so what you're seeing right now is actually the water vapor from the air condensing because the interface between the liquid nitrogen and the atmosphere is so cold that it's just condensing the water vapor in the air. Going back to our experiment here with our racquetball and our liquid nitrogen, we know that if we have it just in normal ambient conditions, if we drop it, it'll bounce, not explode. What do we think will happen when I take this racquetball and I drop it after I've frozen it in liquid nitrogen?
Should explode.
It should explode. This time for sure. Okay. Do we have any other guesses?
It's probably gonna crack.
So we have a crack and an explosion, yes. Anyone else?
Not bounce?
It'll not bounce. Okay, so lots of guesses. But here we're scientists and we like to do experiments. We don't like to just make hypotheses. So I'm gonna go ahead and do this experiment here. Okay, you ready?
Let's do it.
So I'm gonna do a 3, 2, 1 and then drop it. Do you wanna take bets on if I'm actually gonna hit that plate or not? I've 100% missed the plate and like ruined it.
This is a real experiment.
Okay, ready? 3, 2, 1. Whoa.
It did explode!
Nice.
I was right.
What happened?
It exploded.
It literally exploded. I'm just gonna show it up to the camera.
No.
Surprise! It did actually explode. When I dropped it and it hit the plate, what did it sound like?
Glass or something.
It sounded like glass, right? It sounded like if you take a coffee cup and you drop it on the ground and it smashes everywhere like a ceramic. And so that's because the fundamental way that the spaghetti noodles of the polymer were arranged on an atomic level changed. The properties of the material changed when we doused this in liquid nitrogen. And so instead of our polymer spaghetti noodles being kind of all uncooked and wobbly, when I threw it in the liquid nitrogen, those polymer spaghetti molecules actually kind of turned to uncooked spaghetti, if you will, which is why when I dropped it, it shattered. So now, got your tennis ball. This tennis ball is made of the same material as our racquetball, the same exact polymer. So when I douse the tennis ball in liquid nitrogen, what is going to happen when I drop it?
This is a trick question.
The same
It
thing?
exploded.
You guys are suspicious?
Well, you didn't really drop it. You like slam dunked it. So. So I don't know.
What is gonna happen? All right, I'm done. What happens when I slam dunk this tennis ball? Is it? I don't know anything about sports. I'm an engineer, I don't know. Does anyone else think it's gonna explode?
It's gonna bounce.
It's gonna bounce, it's gonna crack. Well, only one way to find out. Mentally prepare yourself. All right, ready? 3, 2, 1. Ooh. Did it break? No. I'm gonna show it up to the camera. So our racquetball is made of the same material as our tennis ball, but yet when we did the same experiment, the racquetball broke, but the tennis ball didn't. And I'm going to ask you all why you think that is. Think like scientists. Why did the tennis ball not break? Here's a probing question. What's different between the racquetball and the tennis ball? It's fuzzy. Yes, actually. That's right on the money. The surface of the tennis ball has all of these like little hair surface fuzzies on the outside, but the racquetball is nice and smooth. In material science and in engineering, what we say is that the tennis ball has a higher surface area than the racquetball. So the tennis ball has a lot more little things on the surface that are making contact with the atmosphere. And what that does is when I take the tennis ball out and into the air, there's a lot more points of contact on the tennis ball for the tennis ball to warm up. When it finally hits the plate and I drop it, it's not as cold as when I had it in the liquid nitrogen. But since our racquetball has a lot lower surface area, because there's just not that much on the surface, by the time I dropped it and it hit the plate, it didn't have as many opportunities to warm up to the atmosphere, and so it was still as cold as it was when I doused it in the liquid nitrogen. And so even though this tennis ball underwent the same phase change as this racquetball, it didn't break because it went back to its original properties. So there you go.
If you shake a tennis ball, would it break?
I don't actually know. I have never done that experiment, but probably. I mean, probably. I don't know. I mean, one way to find out, I don't exactly know how you would shave a tennis ball.
You like give it a fade or something. I don't know.
Probably. That was really funny. Tomi, I'm gonna have you get on that then. That's your task now. This demo is really cool because smashing things is always really cool. Liquid nitrogen is always really cool. Pun absolutely intended. But I cracked myself. But you know, as engineers, what's the point, right? Like, what's the application? Sure, the fundamental science is cool, but like, why do we care about this? Because something that materials engineers are really good at are seeing why big structures fail and why they break, and then analyzing why that happened, and then designing materials so that it doesn't happen again. It turns out that, alluding to Andrew's demo, it turns out metals can kind of behave in a similar way. And so I'm actually going to hand it off to Andrew. Go science. Okay, you ready?
Let's do it.
So I'm gonna do a 3, 2, 1, and then drop it. Oh, I know, the Tokyo building. All right, ready? Want to take bets on if I'm actually gonna hit that plate or not? I've 100% missed the plate.
Wait, why don't we get a bigger plate?